And our final talk of the session will be by Nader Inan, who's going to tell us about a new approach to detecting gravitational rays via the coupling of gravity to the zero-point energy of the phonon modes of a superconductor.
Alright, hello everyone. My name is Nader Inan, and as was shared by our chair, the title of my talk is A New Approach to Detecting Gravitational Waves via the Coupling of Gravity to the Zero-Point Energy of the Phonon Modes of a Superconductor. So it was previously referred to as just gravitational waves interacting with superconductors, but I just thought that was too boring. I thought I'd throw in zero-point energy, which is really what's relevant here, and new approach. So as you probably know, LIGO has recently discovered gravitational waves, and the Nobel Prize is awarded for that. What we are interested in doing is finding out whether there's a possibility for gravitational waves to be detected in some other way that doesn't require $100 million facilities and such elaborate equipment, something that can just be tabletop type laboratory experiments. So that's kind of the thrust of this talk. There's an essay that I submitted to the 2017 Gravity Research Foundation competition. It received an honorable mention and then was published, or is about to be published this month. So this is kind of a concise summary of what was in that essay. So the ultimate goal we have is the detection and generation of gravitational waves in a laboratory setting. And we have the following questions that we're trying to answer. First of all, do gravitational waves interact with the Bose condensate of Cooper pairs in a superconductor different than they do with the ionic lattice? So I'm going to talk a little bit about how a superconductor works for those of you who might not be so familiar with them. And the second question is, can gravitational waves be reflected by superconductors and thereby parametrically amplified in the lab? So this is kind of an extension of our work. I'm really going to be focusing just on this first question, since I obviously only have 10 minutes to talk about this. So the first question really is a question that if we can answer it in the positive, in other words, if it is possible for gravitational waves to interact with the Bose condensate and the Cooper pair density in the superconductor differently than the ionic lattice, if that is true, then we have a new way of detecting gravitational waves in the lab, and that's what I'm going to expand on. So here's kind of a little bit of a model, an attempt to try to give you a visual of what would be happening in a superconductor. This is the ionic lattice, so it's essentially the lattice of the atoms. And these are the Cooper pairs, which are basically pairs of electrons. They're the free electrons that are producing the currents when currents are driven. So a gravitational wave incident on a superconductor, we postulate, is going to interact differently with the ionic lattice than it will with the Cooper pairs. And that's what I'm going to demonstrate here mathematically. So consider, for instance, if a gravitational wave was normal incident on some superconducting slabs. So this is a superconducting slab. A gravitational wave is an incident right down the center like this. And it turns out that it's going to generate this kind of quadrupole pattern, which I can give you a little bit of a dynamic display what that would look like. It'd be something like this. So the gravitational wave is incident normal, and it's going to generate these supercurrents that follow these kind of hyperbolic type trajectories. Now, what we propose is the following. We anticipate from the mathematical analysis that we've done that the Cooper pairs and the ionic lattice are going to respond differently. Particularly, what's going to be shown is that the Cooper pair densities, the electrons, are relatively rigid, or in other words, non-responsive to the gravitational wave. In contrast to the ionic lattice, the remaining atoms that make up the superconductor follow those hyperbolic trajectories that you just saw on that dynamic display. So what that means is this: since the Cooper pairs are electrons, they're negatively charged, you're going to get a negative charge density on the edges of the superconductor here where the Cooper pairs remain, while the ionic lattice, which is positively charged, is going to follow the gravitational wave. And so as a result, you're going to get a charge separation effect. There's going to be an electric potential that's going to exist in the superconductor that would not have otherwise existed if the gravitational wave had not been there. And that would be our method of detecting the gravitational wave. So this is, again, another kind of a visual, an attempt to try to explain the idea. This here is a superconducting cavity, which is radiating gravitational waves, these red wave fronts. This is the metric perturbation, and it's particularly the transverse traceless part of the metric perturbation. It's essentially representing the gravitational wave propagating and is incident on some other superconducting cavity. And when the gravitational wave is incident on this other superconducting cavity, it generates a stress, it's also a transverse traceless stress, in that essentially receiver cavity. You can think of this almost like a transmitter-receiver type system. So there are constituent equations that govern how these superconductors behave. This is a well-known constituent equation called the London constituent equation, and it tells you essentially these are the the supercurrents that are driven in a superconductor when an electromagnetic wave is incident on the superconductor. So this is well established here. We propose that there's a similar constituent equation for gravitational waves. So here's your gravitational wave field, your Hij tau tau, that's propagating. And what we're proposing is that this constituent equation tells you that this stress is induced in the superconductor in response to this gravitational wave. And the key parameter here is what we've referred to as a gravitational shear modulus. We've given it that name because the gravitational wave has a tendency to cause shears in the material. So we consider this to be a shear modulus that tells you basically how responsive will the material be to the gravitational wave that's incident on it. What we're going to do is we're going to develop this expression formally. We're going to show that the gravitational shear modulus for the Cooper pair density is different from the gravitational shear modulus for the ionic lattice, and it's that difference between the two that's going to lead to the charge separation effect that I showed on a previous slide. In other words, positive charges and negative charges will separate in the superconductor in response to the gravitational wave. So we start with what's called the Ginzburg-Landau formulation of a superconductor. For those of you who may not be familiar with superconductivity, you have essentially your canonical momentum, minimal coupling to the vector potential. This psi is a complex order parameter that basically characterizes the Cooper pair density. So we're focused only on the Cooper pairs here with this expression. This alpha and this beta are unique to the particular type of superconductor you're working with. For instance, in our lab we work with niobium. So there's a particular value for alpha and beta for niobium. Now, what we want to do is bring in gravity. So what we did is we embedded this expression in curved space-time, and after kind of turning the crank on some of the mathematics, you discover that the expression turns out to look like this. Notice you still have your kinetic term with minimal coupling here, so this is essentially the same thing you have there. You also still have these phenomenological parameters alpha and beta, but what's new is now you have this coupling to the gravitational wave here. So this is the new term here that tells you how the Cooper pair density is going to interact with the gravitational wave that's incident on the superconductor. Now, what we propose is that if the Cooper pairs are in a zero momentum eigenstate, so they act like a Bose-Einstein condensate when they're in that state, then the complex order parameter takes on this form. And what we did is we used the Helmholtz free energy density, particularly with this term that involves the stress induced in the superconductor related to the gravitational wave strain field. So it follows, you can see it actually, that if you were to just basically, if you wanted to figure out what this stress is, you take the partial derivative of the free energy density with respect to the strain field, and that's going to give you the stress. Now, on the previous slide, I had the expression for the free energy density, so we went ahead and just inserted that in there, took the derivative, turned the crank, and you arrive at the constituent equation that I proposed. The interesting thing is not only do you arrive at that constituent equation, but you also arrive at an expression specifically for this gravitational shear modulus, which tells you exactly how stiff the Cooper pair density is in response to the gravitational wave. So again, turn the crank on some more math, and you find that the gravitational shear modulus has this form, which you can clean up a little bit. You can combine this alpha and beta parameter into a single term that involves what's called the coherence length of the superconductor. And so for those of you who might be familiar with the superconductivity, that tells you essentially how stiff the Cooper pair density is for the superconductor. Now it turns out that this expression is valid for both plus polarization and cross polarization gravitational waves. So we're going to pause on this for a moment. This is the Cooper pair density, and we're going to shift our attention now to the ionic lattice. So for the ionic lattice, we started with the following quantum harmonic oscillator Hamiltonian, which I'm guessing most of us who've done some quantum have seen. You have your typical kinetic term and your harmonic potential here, but you have this extra term involving the coupling to gravity. Okay, so again, we've brought in the gravitational wave there. Now, it's a little bit complicated to try to get energy eigenvalues here because this is a time-dependent perturbation. But it's a periodic time-dependent perturbation, and in that case you can arrive at what are called quasi-energy eigenvalues. It turns out that the quasi-energy eigenvalues, in terms of the phonon modes, so alpha represents the phonon modes, and n is your typical occupation number. So this is in the x direction, the y direction, and the z direction. And so you have your usual h bar omega times n, and your h bar omega times a half being your vacuum energy. But the interesting thing is you have these extra terms here involving A+, where A+ is the amplitude of the gravitational wave. So what's happening is the gravitational wave is changing the energy values of the phonon modes in the superconductor, and not just all the modes involving n, but notice that it's also multiplying to 1/2 h bar omega. In other words, it's affecting the vacuum energy of the superconductor. Hence the title of the talk is that this is an effect associated with the gravitational wave interacting with the vacuum energy of the phonon modes of the superconductor. So we've actually ventured to say that this is, in a sense, a new dynamical Casimir effect. For those of you who might be familiar with Casimir effect, it involves the vacuum energy. And so we've referred to this as a gravitational dynamical Casimir effect. So I'm going to cut to the chase because I guess I have, what, -2 seconds? Okay, so I'll cut to the chase, and it turns out that, turn the crank on a little bit more math, and what you end up finding is that there is in fact a difference between the way the Cooper pair density and the ionic lattice responds to the gravitational wave. This is our punchline. We concluded that there is a 1% effect where if you take the gravitational wave, 1% of that amplitude is going to tell you essentially the strain that you get between the Cooper pairs and the ionic lattice. So there's a sensitivity, there's a paper by Blair. He has shown that there's a sensitivity of 10 to the minus 19 that can already be achieved in the lab. So what that would mean is we could detect gravitational waves on the order of 10 to the minus 17 if they were incident on a superconductor. Thank you.
Hi. It turns out that my field is measuring solid-state ionic crystals, and I've worked with people from University College London on looking at the defects within a crystal. So I do not doubt this, but in a real-world scenario, how would you get rid of the exciton, the trapped exciton, the bulk phonons, which create huge amounts of noise, even more so than at LIGO?
That is an excellent question. So I suspect that possibly some of those answers might be found in this paper by Blair. He gets into a lot of the details concerning experimental measurements and the systemic errors and things of that nature. I'll be totally honest with you that being much more on the theoretical side, I focus much more on the mathematics that leads us to these conclusions, and I don't honestly know the ins and outs of the experimental issues that would come into play in trying to perform this kind of detection. So that's the classic theorist answer, right? I did the theory, I plugged in the numbers, and so we have to work with experimentalists to try and figure something like that out. Yeah.
Do you have any other? Yes.
So what type of scales are we looking for on this? Would we have to have large amplitudes of gravitational waves and large large portions of superconductors in order for this to be measurable?
That's another great question. So the numbers that we use to arrive at these results involve the superconductor on the order of centimeters, edges, and millimeters in depth. And it turns out that what we find is that the relative strain between Cooper pairs and the ionic lattice, so in other words, how far apart they separate from one another, is going to be approximately 1% of the amplitude of the gravitational wave strain field. So if the gravitational wave strain field is, say, like, as I mentioned, 10 to the minus 17, for instance, then the separation is going to be on the order of 10 to the minus 19, which, shockingly, according to Blair, where experiments are actually being done, I believe it's in Australia, they have a sensitivity on the order of 10 to the minus 19, which would mean a gravitational wave on the order of 10 to the minus 17 could potentially be detected via this phenomenon.
Okay.
That's an old paper.
Oh, is it?
Yeah, we've
Well,
updated that.
22 years.
Yeah.
Yeah.
We updated that in this century.
I would love to learn more about that. I would. This is the best I could do in finding something that related experimentally to what we were doing theoretically.
All right, let's thank our speaker again. And I'd like to thank all the speakers in this session, and this session is now closed. If you're going on one of the lab tours, please remember they're meeting down by the registration table at 4:30. And can I get the score sheets from my judges, please?
I had to abstain from Tim.
He was, Nader, you're a grad student, right?
I worked with
So I had to abstain from Nathan because he was a former student.